Hello everyone, so welcome back. Today we are going to cover K nearest neighbor, one of the most intuitive algorithm in all the machine learning. No heavy maths, no complicated theory, just pure logic. Okay, so let's start. What is KNN? Okay, so imagine that you move to a new city and you wanted to know what kind of neighborhood you are in. Okay, so what you'll do, you look at your nearest neighbor. If 3 out of 5 of your nearest neighbor are having fancy bungalows, then you are probably in a upscale area. That's literally KNN. What you need to see is you need to make a new data point. You have to classify it according to the classes. So for that, what you do is you look at the K nearest neighbor of the training data set and say that what the majority of them decided. That will be the class for the new data set point. So that's the complete algorithm. The algorithm is divided into three parts. First, compute distance from your query point to each training point. Second, pick the k closest one. Third, return the majority class among the k neighbors. That's so simple, clear, and powerful. Now, about the first point that you need to compute the distance, we'll move to section 2, the distance matrices. Now, the key question is that how you measure the nearest distance. So there are two matrices. There are more also, but we'll gonna discuss two major. First one is the Euclidean distance. This is your straight line crow fly distance. The formula is square root of the sum of the square difference between the coordinate, thinking of it as a ruler between 2 points. This is the default for continuous data. Second matrix is the Manhattan distance. Instead of going diagonally, you travel along the grid like navigating city block system. You'll add up the absolute difference along each axis. And why this is used, it's because it is robust to the outliners, and in high dimensional data it often works better than the Euclidean. There is often general one more distance which is called as Minkowski distance, which is generally the formula that you are given the Manhattan where p equals to 1 and Euclidean when p equals to 2. To go to infinity, you get a Chebyshev distance maximum difference along any single axis. Okay, but just now we'll look at to these two matrices. For the specific cases, we have the Hamming distance for the categorical or the binary feature, counts how many position have difference in them from the previous position. And secondly, we have the cosine distance for the text data, cares about the angle between the vectors, not the magnitude. Now section 3 goes like for choosing the most important hyperparameter in KNN, that is k. Okay, so let's think. K equals to 1. You only look at a single close neighbor, your decision boundary becomes jagged and noisy, and the model memorizes the training data. It includes all the noises and the outliners. Secondly, first of all, this case is part of overfitting high variance. Secondly, when k equals to n, when n is your entire data set, every prediction just return the majority classes of the whole training set. The model ignores all the local structures. It become too simple, and this is a case of underfitting, high bias. Okay, so now there's a sweet spot in the middle. Here's how test error behave as k increases. It start high at k equals to 1, comes down to a minimum, then start rising again. As U shape, the bottom of the U shape is also your optimal k. Okay, now how to find it? The final method is the cross validation. Train with different values of k, check which one is the best validation score and use it. Moving forward, we have the concept of dimensionality, the curse of dimensionality. The concept goes like that trips everyone up. This is the one of the most important topic that you need to cover in KNN. Okay, in one dimension, you need 10% of the data. In two dimension, you need 31% of the data. In 10 dimension, you need 80% of the data, and in 100 dimension, you basically need the entire data. So if you look at the model, the main problem is that in very high dimension, the distance between the farthest point and the nearest point become almost the same. Everything looks equally far, so your distance matrix become meaningless. Consequences on KNN is the distance stop being discriminative. You need exponentially more data. KNN practically breaks down beyond 20 or so other features. Okay, so now here comes that how you can solve it out. Before applying KNN to high dimensional data, reduce dimension using PCA, feature selection, or autoencoder, or switch a or switch to a parametric model that can handle high dimensional better. Okay. So now let's move for KNN for the regression part. KNN works for regression too. Instead of voting, you average it out. For a new point, find the k nearest neighbor, then predict the mean of their target values, and that's it. If you want even better result, use the weighted averaging. Weight each neighbor value by 1 over its distance, so closer neighbor contribute more to the prediction. Section 6 contain the feature scaling, critical point that people get wrong most of the time. KNN is 100% based on distance. So if one feature range from 0 to 1000 and another range from 0 to 1, the big scale feature completely dominate every distance calculation. The other feature become invisible. You must scale your feature before KNN. Three options are: first one is the min max normalization. Squeeze everything between 0 to 1, good when you have no extreme outliers. Second is the Z score standardization. Subtract the mean, divide by the standard deviation, and this is default go to. Third one is the robust scaling. Use median and IQR instead of other techniques. These are best when outliners are present. Section 7 contain of speed, brute force versus the smart structure. That's a very quick topic about the efficiency. Brute force KNN checks every single training point for every query. That's O of n times D per prediction, slows for larger data. Okay, now the smarter option are KD tree, works greater for the low dimension under 20 features, bring query down to roughly O of log of n on average. Second one is the ball tree, handle the high dimensional and non-Euclidean distance better. Third one is the HNSW and FAISS for the massive scaling approximation nearest neighbor search. Concluding it all, we have seen that KNN is a lazy, no training, all working at predictable data technique. Distance matrix matters here's the most, and in some of the cases when we have the high dimension, the distance matrix also fail. So for that we have to go for the PCA and autoencoder and dimensional reduction techniques. Okay. Now for the regression also we have seen about some of the part that how KNN is being used in regression. So that's all from my side. Thank you.